Okay, let's get started. My name is Megh Krishnaswamy, and today we will be looking at natural language processing um, for text mining and sentiment analysis. Uh, although, given the limited scope and given the vastness of the NLP landscape, we will be limiting ourselves to one tool, which is the Spacey NLP toolkit. And we will be looking at a small task where if we already have text you, for our use case, we'll be looking at some of the data cleanup uh, pipelines that we can use in order to carry out one specific NLP task, right? So the materials for today's workshop have been added to chat. So if do click on the wiki page, that should take you to a page that looks like this. All right. Now, what is Spacey and what can we do with it? Right now, Spacey is a Python toolkit that has been primarily built with Python, right? And it contains a whole bunch of code bases that one can run for multiple languages. Right now, one of the biggest libraries and the most popular ones tends to be the one for English. This is primarily because almost 99% of all NLP research, as well as 90% of all linguistics research, is done on English. Uh, However, Spacey also has approximately 20 to 25 other languages which have pipelines that could work with for a varying degree of complexity as far as tasks are concerned. Now, when we process text with Spacey, what Spacey does is pass the text through its language model. It extracts a vocabulary or a list of words, which are each assigned a unique hash value and are stored as a string. These are processed with the Lexeme pipeline. Uh, the text that we share is also tokenized. So Spacey will read all the text that you provide, identify spaces, and identify individual words, which will all be assigned, which will be processed along with the vocabulary to make sure that every word and its meaning and all of its grammatical components are correctly identified. Um, Now, after all of this processing of the raw document, of the raw text that we give is done, Spacey creates a document of its own. And in this document, it is able to identify tokens, and it's also able to identify spans, which are user-defined strings, which may contain one or more words, one or more sentences. Once all of this pipeline is done, we can carry out all sorts of natural language processing tasks, and we can essentially use all the text strings that we've provided in the form of data. Right now, Spacey has a lot of wonderful resources on their own website. So I invite you to check out the resources section of our wiki page, where you'd be able to learn more about the different models that Spacey has, what the Spacey universe contains, and if you're into building your own API, what are your options? Now, I have to correct myself. There's support for 75 plus languages. However, trained pipeline, which can help you carry out various NLP tasks, are available currently for 25 languages, but uh, sky's the limit. Now, there is also a little bit more about the library architecture, and there is a link in the wiki page that can tell you more about all the different terminology that Spacey uses. And I will try to cover some of this in today's workshop. All right, so let's get started with our code base. Now, right on top of our wiki page, that you will notice a link that leads to the Google Colab portion of today's workshop. Once you click on it, it should take you to this page where our code lives. I've added this to our chat. And as soon as you click on the Open in Colab button, it should open our code base in Google Colab, as always. All right, so let's begin with the fundamentals of natural language processing. First up, this is a field that uses machine language technology. Why do we use it? It is used for automating all sorts of language tasks, which include the interpretation, manipulation, and comprehension of human languages. One of the purposes include in artificial intelligence, but some of the other purposes are information extraction, cleaning, database management, and the works. Now, our assumption here is that all of the tasks where a machine needs to work with natural language, if we are able to provide our machine with a statistically viable predictions about the text that we are giving it, this should automate most of our tasks. Of course, with the availability of large language models like ChatGPT, we know that providing statistically viable predictions can go a long way. We can now produce near human text. We were able to provide responses and using basic prompts, and it's gone a long way. Now, NLP combines the expertise and domain language from a whole bunch of fields. So it's not just statistics or machine learning. There's a lot of linguists involved. Now we have more deep learning architecture involved. We have all kinds of complex math, which runs the back end of most of our natural language processing tasks. And the NLP applications that are fairly popular include sentiment analysis, information extraction, all kinds of cleaning tasks. And we've moved from just working with human language to working with drug discovery and looking for new genetic sequences, because as long as we have some kind of statistics powering some kind of prediction task, the sky is the limit, right? Now, as far as large language models are concerned, they treat natural language processing with a maximalist approach, which means just use an extremely big systems in order to process tasks, be it a small task or a big task. And sometimes, depending on the task, we might need a more refined approach. And that's where our NLP toolkits come in, such as Spacey. Right. So think of Spacey, think of a large language model like ChatGPT as a jackhammer, and something like Spacey as a Swiss Army knife. We want something, we want a delicate approach. We want to make sure that we're using our resources effectively, and we're understanding different modules that make up human language, right? So today we'll be looking at some of the tasks that Spacey can carry out for us. The first one is tokenization. So how do we actually segment a document into words, into punctuation marks, into spaces? Next, how do we clean up our document to remove things that are not carrying any information, such as stop words and special characters? Next, we'll be looking at lemmatization, where we want to extract the meaning of a word without the morphological add-ons that a word contains. And finally, we're going to take a look at Spacey's similarity calculator and see how that works out. Right. Next. I've talked a little bit about how the Spacey library loads your document, and there's a little pipeline, the images from the Spacey website, where we provide a text, and it goes through the tokenizer, and then we get parts of speech tags, we get a parse, we get the named entity recognition pipeline, and once all of this is done, the output is a document that's going to give us as much information as possible about every word in our document and the relationship that these words share with each other. All right, So let's get started with loading up our Spacie library. So for this, you'd need the import Spacie code line. And in order to run, Spacie needs a library. And so we're going to use the spacie.cli.download. So we're going to use our command line interface to download the English medium library. So there's a full list that you can access using the spacie.io usage models that'll tell you about all your options. Today, we're going to use the MD or the medium-sized English library. There's also small, there's also large. Because we're not using a very high intensity task today, the medium-sized library should be all right. All right. Now, once we have our English library downloaded, we want to load up the the pipeline for English and run a little test. So here I've provided a little sentence on the horror genre. And if you are able to run this code chunk correctly, it means that your library has been identified. And if provided with a sentence, Spacie is able to identify the first 5 tokens within this sentence, right? So that's what's happening here. All right. Now, just some terminology about how strings are processed by Spacie. So if you throw a bunch of text at Spacie, the output of the pipeline, it's termed as the document. As a user, if you decide to ask for a chunk of a sentence or a chunk of text, that's a span. A span could contain 1 or more tokens. Now, if your span begins with a capital letter and ends with a period and is identified as a meaning containing string, then this is labeled as a sentence by Spacie, and Spacie does automatic sentence detection for you. Then we have the vocabulary, which is just the data entries of every word, and every word in the Spacie vocabulary has a unique hash. Finally, we have a lexeme, which is the label for every unique entry within the vocabulary. All right. Now, let's try a longer span over here. And at this point, I invite you to, I've printed a certain token from this chunk, but I invite you to take a minute or two to maybe query other tokens which are present at other locations in this text, see if things work out.
There's counting from 0.
Right, yeah, of course. And since we are working on Python, the count starts from 0 and not 1. Okay, so now let's look at some spans and sentences. In order to call a span, all we have to do is tell Spacie to print a certain string of tokens. So in this case, my span is the first 10 tokens provided in Spacie. That Spacie has processed in the document that we provided it. The document being this paragraph from the origins section of the horror genre Wikipedia entry. Now, I also want to identify all the sentences that are present in this document that I have given Spacie. So if I run this, it's a little for loop that prints 1 sentence at a time, so I can look at them. Now you'll notice that the first, if we compare our document up here with the sentences that have been printed down here, you'll notice that every sentence that is present in our document or is being printed down here. So we have some very long sentences, so you might need to scroll to the right in order to identify them. All right. The next, we know that all of our document has been processed, and each token in our document has now been identified within the vocabulary. And now if we want to know the hash number or the unique identifier for the word beings, we will call this using eng.vocab.strings. And just to explain the code here, English is just the eng is just the variable that I have used to name the English spacey library that I downloaded. I'm going to call the vocab within the language library that I downloaded, and then ask it to process a string for me. Right. So if I ask it to process, if I ask it to print the hash for me, I get this very long string of numbers, which is the unique identifier for the word beings. And you can try this out for various words right here. Sometimes hash numbers are very useful in case we want to use a unique identifier instead of using the number themselves, using the word itself. Right. The next thing that we might need to query while working on an NLP task is whether a given token is a real word, or if it's not a real word, or it's a special symbol of some kind. So in order to carry out this task, we call a token, and we use the is_alpha method in order not method function in order to assess if our given token is alphabetical, alphanumeric, or if it's a special symbol. Right. So if you run this code, it's going to look within the first 15 tokens in our document, and it's only going to print the tokens which are real words and are not symbols. Right. Now, besides is_alpha, we have a few other functions. One of them is underscore punct, which checks for all the punctuation marks within a given text. So if you'd like to take the next 2 minutes in order to edit the print function in the previous code in order to print all the punctuation marks in our document, I invite you to give it a try. Rather than copying and pasting, it might be worth it to actually type out the code. And this way, you can let me know if this code works for you or not. Right. So it's 3:22. I'll wait till 3:24. And if you have the right answer for how we can search for all the punctuation marks in our document, or please let me know in chat. Awesome. Yeah. If you know how to extract all the punctuation marks in a given document, please do type out your solution in the code. So in our chat, so I can see how you're going about it. Now here, I only called the first 15 tokens. You could call more than 15 tokens. You could call the first 5 tokens. Completely up to you. Nice. So Simone, I'm going to try and run the little code line, the code that you ran here. Now here you're looking through 50 tokens, and I'm going to run it without carrying out any checks. Right. So as it happens, our document does contain 50 tokens, and so the code ran without trouble. But if when we hard code a number like this, it might be worth it to make sure that we know how many words are there in our document, because otherwise we might run into an error, right? And how do we count how many tokens are there in our document? I leave that up to you. But if you'd like to know how to do that, do let me know before our session ends, and I can tell you how that would work. Okay, so we know how to extract punctuation. We know how to extract alphanumeric strings. And now we're going to move on to processing linguistic features that are associated with the tokens that spaCy has extracted for us. Now, it's important at this point to remember that once we pass a document through spaCy, once we pass some text through spaCy, it becomes a document. And whatever output is received out of spacey, it's going to be in the form of tokens, in the form of sentences, in the form of linguistic features, right? We're no longer dealing with strings or special characters. We're actually dealing with different with the linguistic hierarchy associated with text, right? So the first thing that we want to do is we want to see what unique lemma are available in a certain portion of our text. So I'll run the for loop in the code chunk under lemma first, and then and while it runs, I'll give an explanation for what I did. Right. Now, the first thing to note here is that we have a little, I'm calling a function over here, lemma underscore, right? And what lemma underscore does is it takes a given token that spacey has identified, and it looks for the meaning of that token. It scrubs the given token of all of its capitalization. It removes all the morphology. So if for example, the token origins, it is the lemma is origin, and we've added the inflection for plural. So we've added an S to it. Now, the base meaning, the core mental entry for origins and origin is much the same. And so when we extract the lemma, we see that all of the morphology has been scrubbed out. For the first token, capital T, we see that the capitalization has also been scrubbed out, right? So when it comes to lemma extraction, the only thing we're interested in is the meaning. All right. Now, the next thing that we might be interested in is what's the part of speech that is associated with a given word? Is it a noun? Is it a determiner? Is it a verb? Is it an adjective? Where this is pause tagging is very useful when it comes to information extraction, because something that that a lot of linguists know from research is that often nouns and verbs may carry the load of meaning in a sentence more than, say, the determiners and adverbs and some of the other parts of speech. And so when we perform an information extraction task, knowing what kind of word we're dealing with is very important. Now, in order to extract the pause tag and the pause label, we're going to use pause underscore and dot pause. So we have the pause function and the pause underscore function. And I will run this, and then I invite you to examine the code and tell me in chat what you think is the difference between pause underscore and pause, the two functions that are here. Now, just to explain the print statement, the first thing that it prints out is and then it prints out the dot pause, the output of dot pause, and then it prints out the output of dot pause underscore. And you might notice that there's something different about the pause tag and the pause label over here. So I'll give you about 30 seconds if you have an idea of what you think is the difference between a pause tag and a pause label. Please let me know in chat. Well, so let me answer. Spacey likes to store the parts of speech identification information in two ways. One is for every part of speech tag, Spacey has a unique integer value. So we have the label determiner, which is stored as pause tag number 90. Then we have nouns, which are saved as 92. Verbs are saved as 100, right? So it's just a way of, when we use pause and we use underscore, it's actually extracting a little string for us, which is which tells us if it's a determiner, a noun, or a verb, right? But often, because we are dealing with a computational process, numbers are often more useful. And so when we call the dot pause, when we use dot pause to call the tag, we get a number. And if we query the label using dot pause underscore, we get the label, right? And this is something that you might have noticed in the previous code as well. If we notice, we ran lemma underscore, and we ran dot lemma. So dot lemma underscore is giving us the label assigned to the given lemma. And when we run dot lemma, it just gives us a long string of numbers, which is the unique identifier for the given lemma. Right. So it's just a little quirk in how Spacey likes to process different data entries. All right. Next, we want to look at syntactic dependency. So in a given sentence, words are arranged in a certain kind of hierarchy, and the words inside a sentence are not they're not just they don't exist in a bag of words model. They have some kind of inherent relationship with each other, which allows us to use words to build a sentence. And so if we want to understand the relationship between different words arranged within a given sentence, we need to query syntactic dependencies for the different words. All right. So in order to query the dependency, we will use .dep underscore as the function. And I've created a little for loop that does this for us. And in this case, it's going to look for it's going to go into the list of sentences that we generated a couple of code boxes ago. It's going to look at the first sentence, and it's going to look through every token within the sentence. And it's going to give us a little table in which we have the part of speech label, we have the syntactic dependency information, and the actual token itself. So if you run this little code box, you're going to get all of the words in the sentence along with all the special characters. Remember, I did not clean up our sentence because syntactic dependency also gets information from punctuation mark, from punctuation. And if you notice, each of the special characters, each of the punctuation marks have the label punct because they're punctuation. Then if you look through the listing, you'll notice that the nouns and verbs have been marked under the dependency column, and the head for every token is also listed. So you have the subject, noun subject, you have preposition, and so on and so forth. There's a lot that can be discussed as far as syntactic dependency is concerned, and if I'd love to do a session sometime on it. But for now, just sometimes NLP requires us to understand our sentence and query it more deeply, and this is how we would do it. Next, when it comes to information extraction, one of the things that we might be interested in is named entities. So things that objects or entities which have a unique name. And if we want to identify all the entities in in a given sentence, we could use that with the .ents function. So if you run this, it should give you the text, and then it should give you the token label. 1 second, let me double check. All right, so for the given sentence, 1 minute. These manifested in stories of beings such as demons, witches, vampires, werewolves, and ghosts. There are no named entities. However, if this sentence included the name of a vampire, or it included the name of a specific werewolf or the name of a specific witch. So if we had, say, Sabrina, or we had Lesat, that might be something that would show up if this code is run. All right. Then, while processing our text, we may also need to remove stop words and punctuation. Computation is often very expensive. So if you have a large document which has, say, 5 million tokens, and you want to perform information extraction on it, running the entire document through your pipeline may be very expensive. So one of the ways in which we can make our process more efficient is by removing the words that don't really contain the meaning of our given sentence. And in order to do this, we can identify stop words. So the first up, we want to load all of the stop words from Spacey's stop word dictionary, which I have done in this first line of code. And then I want to use the first, I want to go through the first 10 tokens and identify all of the words which are not stop words and which are not punctuation, right? So that's essentially what this for loop is doing. Right. So if a given token is not in the stop words list and it's not in the punctuation list, it'll get printed here, and that's what happens. Next is we've talked a lot about the different tags, the pause tags, the syntactic dependency tags, and what if as non-linguists, some of you want to know more about what this code means. Spacey has a little code base called explain, and if you run spacey.explain and provide it with one of the tags, it will tell you more about it. Right, so just remember to correctly type out the label associated with whichever tag you're looking at, and Spacey will provide whatever other explanation is available within its engine. Okay. Yeah, Pradnya, that's a good question. Let me just double check make sure I didn't do anything. I think in this specific case, it's not being treated as a stop word because the is capitalized. So I would run this pipeline one more time with maybe uh, without the capitalization, and it's possible that that may affect stop words. Now, since Spacey tends to be quite literal, and often capitalize words, even if they have the same spelling as an article, might be unique words, and I think that may be one of the reasons why Spacey is returning the. Right? I invite you to maybe go back to our text and not remove the capitalization in the and run this again, and let me know what happens when you do that. Okay, so similarity calculator, it's just a little code chunk that Spacey has. It may be useful to a small task, or it may not be, but essentially it's going to use mathematical representations of every word in the vocabulary, right? And then use an algorithm in order to examine if if a bunch of words in two given spans are similar to each other or not. So in this case, I've provided the two documents: I like horror movies and I like scary films. Right, I've passed both of them through Spacey. So these are two strings that I provided. Once I pass it through the Spacey pipeline, they become documents. And I want to know how similar these two are. And so when I run these two, notice that their syntax is very similar. They have two words in common, and then there's a certain amount of similarity between the words horror and scary and movies and films, right? And so this returns me a 96% similarity, right? I invite you to try out some of the other sentences and see how this works for your given task. And in order to give you a chance to do this, I've added two more spans over here. So slasher is a genre of horror. Body horror is a type of scary movie. And I'd like you to maybe, if you have a few minutes, to make changes to the code in the previous code box, and let me know what similarity score you get for span 1 and span 2. You will need to uncomment these two lines, the last two lines of this code box, and make some kind of changes to them.
The similarity is computed based on the label number that two words have.
Yeah, so it uses embeddings. Spacey has its own way of creating word vectors. And so every word there's a relationship between every word and all other words. And so it uses word level similarity between all the tokens into given spans to figure out if sentence one is similar to sentence two.
So there is a semantic.
Yeah, it's going through. Now in these two sentences, there are also identical words which are present. So the similarity score will be high also because it's using the same words. Okay, so I'm gonna move on from this. If you'd like to know how to do it, it's all we have to do here is if you notice the code, right? It's just doc1, doc2, right? All you have to do is query doc1 span1 dot similarity and oh, I tried but failed. Simon, could you tell me what you added or how you arrived at your um, I'm sorry. Yes, so I mean, it's the span one and span two is just they're just variable names that I provided. Uh, what we would need to first convert them into documents, as you said. Yes, that's correct. Right. So in order to solve this, first we will need to create documents out of the strings that we provided. So you might want to do something similar to this. So doc1 equals, and then you call the English spacey pipeline, and then you tell it to process span1 for you, right? And then once you have a document created out of each of the two spans, then that's when you'll be able to run the next couple of lines. Okay. Cool. Yes. So you got an 87% similarity. Yep, that sounds about right. We have some words which are being used. We also have words like genre and type, which tend to be closer to each other than many other words. We also have scary movie versus horror, where there's also some similarities in words. We also have syntactic similarity, right? So all of that will contribute to this, right? Now, with spacey, you can also extract vectors for different words. A vector is a mathematical representation for a given span or token. And if you ran the pipeline that I've provided over here, you'll get a large series of numbers, and these essentially represent the phrase horror is horrifying. Okay, now we can also search by pos tag. There's a bunch of searches that you can create if you'd like to look for if we have two documents over here, that love is obsessive, you love me, and within this, if you'd like to find out if there is similarity in the lemmas that are available here, you can run you can search through them using the dot lemma underscore and the dot pos underscore, right? So let's just take a look at what we're doing here. First, we're simply printing out the lemma and pos labels for the documents that I've provided over here. Next, I've simply created a little function that's looking for the token love within the lemma for a given token, and it's also looking for the verb form of love. So it's going to assess these two sentences and figure out which sentence contains the lemma love and where love is used as a verb and not as a noun. And so when we run this function, it's going to say that document one is not a match because in document one, love is a noun and not a verb. But document three is a match because here we're using love as a verb, right? So, and if we want to disambiguate our text using pos tags and the lemma labels is a great way to make sure that a word which looks identical in two different contexts can be disambiguated using linguistic features. Okay, now having gone through some of the available tools, let's do a quick project. Now for today, we're going to go through a text corpus, which is the IMDb movie review corpus, which contains about 50,000 movie reviews. So however, we don't have the it might take too long to run through 50,000 movie reviews. So we're going to use a small subset of this mm, uh, database with 1K reviews. So if you click on the first code base, uncommented code base, it's going to load up our little database data frame. And if you go through some of the other code bases in this section, it's just going to let you know a little bit about what this code base contains, this database contains. So in our database, we have 3 columns. The first one is just a label associated with each row. Second one, it contains a review, which is just a bunch of text. And the third column contains a sentiment value, so it's either positive or negative. Now, because for today's use case, we've chosen 1,000 random positive sentiment reviews. So these are all movies that have been judged positively, right? And there's also some negative reviews in here. So if you look at and they've been arranged at the bottom of the data frame. All right. And if you'd like to just examine the database, call for some of the reviews, you can do so here. Right. Now, of this 1,000 movie reviews, if we wanted to search for a movie recommendation using the text that is available in the reviews, that's something that we can build a small pipeline for using Spacey. So first, we're going to downsample to 500 positive reviews. So we don't want too many of them. And so if you run the code, the little code base code box for downsampling, it's going to select the first 500 reviews out of the corpus. And next, in order to make our computation, speed up our computation, we're going to remove the stop words because they're not contributing to the meaning of the sentence as much as the content words do. Right. So I'm going to create another data frame which is going to house all the content words in the 500 reviews that we extracted. And we're going to use the is underscore stop and is underscore punctuation functions in order to clean up our reviews. Now this code box may take a little longer because it's going to run through every row and perform our cleanup for us. So do give it a few minutes. And once both of these code boxes have complete their run, so we took about 28 seconds, right? So now our task for today is to together come up with a custom list of words that we can use to search for horror movies, right? We want to search through the review section. We want to look for the words in the title, which may be available in the reviews. And we want to see if Spacey is able to process the review column within the database in order to extract a good movie recommendation for us. Right, so I've made a small list of words that are associated with the horror genre. I invite you to add more words here if you think there may be other words that may yield a better result. So you can remove words from here if you think that they're not if they're not affiliated with the horror genre. Completely up to you. Now, in this section, I'm actually using a phrase matcher, which is a Spacey class for identifying a given set of tokens in a document, right? So the name is fairly self-referential, right? And I need to build a little rule for carrying out my phrase matching. So what do I want? I want my phrase matcher to look through the text in a given document, and then run the Spacey English pipeline for all of the text, and then return patterns for me, right? And if you want to add more matches to a given to the list of phrases that we've already added, you can use phrase matcher underscore add phrase underscore matcher dot add. So you can either add the words to the phrases list in the first code box, or you can use use the matcher.add function in order to add phrases, right? Next, once we are done with choosing all of the words that could be associated with horror, we want to run a for loop that can do the phrase matching for us. So here, there's a little for loop that can run this for you, and it might take a little while because we are looking through 500 documents and making sure that each of them is getting processed, right? And let's see. Let me make sure I've run all my code. Right. So, it looks like I hadn't created my document. So once you run the phrase matcher for loop, it's going to look through all the phrases that we provided in the list of phrases, and it's going to return a bunch of reviews that contain one or more of these phrases, right? And so this is a simple low resource way of using natural language processing in order to get movie recommendations if you want to watch a horror movie today. Now, I believe a similar pipeline can be built for romance, for action, for thrillers. If you want to watch a movie about cars or a movie about planes, or you'd like to do a bad movie night where instead of using the positive movie review sentiment, you can use the negative movie sentiment in order to extract movies that IMDb viewers reacted negatively to. And that's another way to carry out data extraction, right? If you want if you want to perform a named entity recognizer, so you want to look for movies about Canada, or you want to look at movies that feature England, you can search for these using the NER, the .ents function that I mentioned before. So there's a lot of functionality that can help you process your text. And just as we looked through movie reviews, there are all kinds of other documents where you can query your document in order to extract information. Sky's the limit. So besides Spacey, there are also a lot of other Python libraries that can perform similar functions. The reason why we went through Spacey today is because it provides it's a maximalist linguistic approach. It gives you more than one tool for linguistic processing. And think of this as a under the hood look at how large language models work behind the scenes. When uh, instead of just the front end of the ChatGPT chat window that most of us may be querying or working with. All right, so that is all I have for you. There are a few, there's a little test or a little alternate project that I've kind of listed for you. And I invite you to maybe take the next couple of minutes, or maybe take as long as you like, in order to create a custom list for a different genre or for a different kind of movie review use case, right? So I also invite you to look at all of the matches phrase that our phrase matcher pulled out for us, and actually examine it to see if movie reviews are actually a good database for looking for movie recommendations for a given genre. Did we actually, did we actually succeed in our task by using movie reviews, or uh, should we use a different kind of input data in order to carry out our task today? Okay, so that would be, do remember to always examine your data as much as you examine your tools. And yeah, that's all I have. Thank you so much.